Here is another opportunity for all self-coders to test and challenge your skills. So in Project 12, we will deeply analyze the Olympic medals dataset consisting of 3 different datasets. So we have the summer dataset with all Summer Olympic Games medals from 1896 in Athens till 2012 in London. And then we have the Winter Olympics dataset with all medals from 1924 till 2014. And finally, we have the CSV file dictionary.csv with some more information on the countries. So the country code, the population, and the GDP per capita. So first of all, we should merge summer and winter, so to say vertically merge. And we should have one row for each medal awarded in any of the Olympic Games. And then we should save the merge data frame in Olympics. And actually, we should have an additional column like addition that indicates whether the row is coming from the Winter or the Summer Olympic Games data set. And also we should add another column with the full country name from dictionary. So we should add here the full country name with a merge. Then let's go on with data cleaning, and we should actually assign appropriate column headers to the column country codes, for example, code, and for the full country names like a country. And actually, we should also remove white spaces or empty spaces from column headers in the data frames Olympic and dictionary. And finally, for some country codes, we do not have the corresponding full country name, for example, for the code URS, and therefore we have here a missing value in the data frame Olympics. And in a first step, you should identify those country codes where we have no data available and search on the web for the full country names and replace the missing values. And alternatively, you can also find a solution for this here for question 3 at the end of this notebook. So searching for the full country names is here optional. Now let's go on to part 2 of data cleaning, and you should remove rows in the Olympics data frame where the country code and therefore also the full country name is unknown, and you should make sure that you restore the range index. And then you should convert the column medal into an ordered categorical. So we have here the order that gold is better than silver and silver is better than bronze. And with this, we are ready for explanatory data analysis. And first of all, we should identify the top 10 countries in terms of total medals. And here we can simply use the Seaborn plots. So first of all, we should visualize the top 10 countries by total medals. And then by changing only 1 or 2 parameters, we can also split total medals into summer and winter. And already here we could identify which countries are more summer countries and which countries are more successful in Winter Olympic Games. And alternatively, we can also split total medals of the top 10 countries into gold, silver, and bronze. Coming now to the next question, do GDP, population, and politics matter? And to answer these questions, we have to create the following aggregated and merged data frame with the top 50 countries. And here you can see a screenshot with the first 12 countries. So we have here United States, and we have one column with the total medals, then one column with gold medals, one with silver and bronze. And also we have the population that we have to add from dictionary and also the GDP. And finally we have the column total games. And this should show the number of participations. So United States participated in 48 Olympic Games. And actually, as approximation, you should determine the number of editions where these countries have won at least one medal. So these are the absolute values, so the absolute medals and the absolute population and GDP. However, ranks are more meaningful for our analysis. And we should create an additional data frame, so the ranks data frame, where we don't have the absolute values, but the ranks. And it should look like this here. So United States has rank 1 in terms of total medals, and also rank 1 in terms of gold, silver, and bronze medals, and also in the number of participations. Next, we should statistically check whether GDP, total games, and population have an effect on total medals. And we should work with the ranks data frame. And for example, we could check the rank correlation between those features. And we should work here with the Spearman correlation. So this question is a bit more challenging from a statistical point of view. And for example, hypothesis testing is optional. And you can also have a look at the solution. Next, you should create the following Seaborn heat map with the medal ranks for the top 50 countries. So we have here the countries, and we have here the rank in terms of total medals, and the ranks when we only consider medals won by women, by men, and in the Winter Olympic Games and in Summer Olympic Games. And having this aggregation, we can also answer the following questions. So we should identify countries that are equally successful in Summer and Winter Games. And also we should identify typical Summer Games countries and typical Winter Games countries. And the same we can also do for men versus women. And finally, let's create the following Seaborn heat map that shows the ranks of the top 50 countries by sports. So here we have the top 50 countries, and here we have the sports. And the colors indicate the rank of the specific country in the sports. So for example, United States is the most successful country in aquatics. It's green, it's 1. And having this Seaborn heat map, we can also identify traditional sports and national sports for countries like UK and China. So this is the explanatory data analysis challenge. I hope you have fun. And of course, feel free to have a look at the solutions notebook and also the videos with these solutions. All right, in this lecture, we are going to import the data sets into Python and Pandas. And getting the data is not an issue here in this project. So we have 3 CSV files. And first of all, let's import Pandas. And then we have actually a data set on the Summer Olympic Games. Then 1 data set on the Winter Olympic Games. And we have another data set with some more information on the countries. So let's import the CSV files, and we have the variables or the data frames summer, winter, and dictionary or dic. And first of all, let's have a look at the summer data frame. And here we have all athletes that ever won a medal in Summer Olympic Games. So we have the editions from 1896 until 2012 in London. And each and every row here stands for 1 athlete who won a medal. For instance, Alfred Hayos, he won in 1896 in Athens in the sport aquatics and discipline swimming and the event 100 meter freestyle, the gold medal. And he's from Hungary, and it's actually a man. And we can also get some meter information with the info method. And in total, we have over 30,000 rows or athletes. And in total, we have 9 characteristics or attributes. So we have the year, city, sport, discipline, athlete, name, country, gender, event, and medal. And obviously, missing values are not an issue here. So we only have 4 missing values here in the country column. And in the year column, we have actually the year, which is here an integer. And in all of the other columns, we have text or string data. Now let's come to the winter data frame. And actually, the structure here is pretty similar. So we have the Olympic Winter Games editions from 1924 till 2014. And again, each and every row is here an athlete that won a medal. So let's get some further information here. And obviously we have no missing values at all, and in total we have 5,770 medals. And again, we have 9 attributes or columns. And finally, let's have a look at the data frame dig with some more information on the countries here. So here in the data frame summer and winter, we only have the country codes like FRA for France. And here we have some more information. So we have the full country name, then the Olympic country code, the population, and the GDP. And actually GDP stands for gross domestic product. And GDP per capita is a measure of a country's economic output that accounts for its number of people. And that makes it a good measurement of a country's standard of living. And let's also call the info method here on this data frame. And we have in total 201 countries. And we have 4 columns. And we have some missing values in the columns population and GDP. And we can also get those rows and those countries where we have at least 1 missing value. And typically these are smaller countries or countries like North Korea, where we do not have any information on the GDP, or for some countries also on the population. Alright, thanks for watching, and see you in the next lecture. Bye. Alright, in this lecture we are going to perform 2 data merges. First we merge, or more precisely we vertically concatenate the data frames summer and winter into one data frame. And second we perform a left join to add the full country names that correspond to the country codes. And first of all, let's vertically concatenate summer and winter. And this is not a big issue because we have the same 9 columns in both data frames. And we can use the direct pandas method pd.concat. And we pass a list with the 2 data frames, summer and winter. And actually we pass 0 to the axis parameter to vertically concatenate. So we actually have all rows of the summer data frame and add all rows of the winter data frame. And still we want to have for each and every row the information whether the row is coming from the summer or the winter data frame. And therefore we pass a list summer and winter to the keys parameter. And by doing so we create an additional column with that information. And the column label should be addition. So let's have a look what we get here. So here we have all rows of summer and all rows of winter in one data frame. And actually here we have an additional index level, the outer index level, with the information whether the rows coming from the summer data frame or the winter data frame. And the index name is here addition. And we have here a multi-index with 2 levels, but actually we simply want to have the addition as column, and therefore we can reset the index and create a range index. And here we have the column addition, but still we have the former inner index level, level 1, and we simply drop this here. So now we have the column addition and a range index. And now let's save the concatenated or merged data frame in the variable Olympics. And here we have included all medals and all athletes that won at least 1 medal in Olympic Games. So no matter if it's summer or winter. Now we have here the country codes, and it would be more intuitive and helpful to also have the full country names. And as you might remember, we have the full country name here in the data frame dig. And we have actually here the full country name and also the code. And this looks like a left join. So we perform a left join on the left data frame Olympics. And the right data frame is here the dig data frame with only the columns country and code. And actually we use here the merge method, and we pass left to the how parameter. And actually we want to perform the left join in the left data frame on the country column. Here we have the country code. and in the right data frame on the code column. So let's have a look how it works. And here we have actually now country X, country Y, and code. So essentially we have the country code twice, and therefore we can drop the column code. So now we have the country codes in the column country X and the full country name in country Y. And let's also reassign Olympics with this left join here. And with this we have successfully merged and concatenated the data frames. And in the next lecture we will actually clean here the data. So for instance, we could change the column labels here. So country X and country Y isn't really the best solution here. So thanks for watching, and see you also in the next lecture. Bye. In this and the next lecture we are going to clean the data sets, and let's start with the Olympics data set. And we have seen in the last lecture that we have country X and country Y. And it's better to rename those column labels and, for instance, use code and country. And of course, we can do this with the rename method. And we pass here a dictionary with two key value pairs to the columns parameter. And the key is always the old label and the value the new label. So now we have the two new labels, code and country. And of course, we pass true to the in-place parameter. Next, let's have a look at the dict data frame, and here we have the column label GDP per capita, and we have actually two white spaces here, and white spaces in a column label is always not the best solution, and we can simply call this column label here GDP. So let's rename the label. And now let's come to missing values, and in the Olympics data frame we have some missing values, and obviously we have over 6,000 missing values in the country column, so that's the full country name. And actually we can filter the Olympics data frame for all rows or for all medals where we have a missing value in the country column to understand why we have here missing values. So here we have missing values in the country column, and these are only 10 examples. And for instance, we have the codes ZZX, EUN, and TCH. So we do not have any full country names for these codes. And first of all, let's save the index label for those rows where we do not have any information on the country name in the variable missing country index. So later on, it's easier to get those rows again by just passing here the index labels to log. And here we're starting with 132, 133, and so on. Next, let's have a look at all country codes where we do not have any information on the full country name. And actually, we sort the country codes by the number of occurrences from high to low with value counts. And here we have URS, and that stands for Soviet Union, followed by GDR, which is German Democratic Republic, and so on. So obviously, these are countries that do not exist anymore, and therefore in our dict data frame, we do not have the corresponding full country name. So this is here now a panda series, and in the index we have the codes where we do not have the full country name, and let's save those codes in the variable old countries, so that doesn't exist anymore, starting with Soviet Union, GDR, and so on. And now our task is to find additional data sources where we can find the corresponding country names here. And actually I did a very quick Google search, and actually I found the corresponding country names. And next I create a mapper panda series with the old country codes here in the index. And actually here as data, we pass a list with the corresponding full country names. So the country name corresponding to URS is Soviet Union. Then we have East Germany for GDR. Then Romania for ROU. and West Germany for FRG and so on. So let's create the panda series mapper, and let's have a look here. So this is an ordinary panda series with on the left hand side the country codes and on the right hand side the full country names. And now in our Olympics data frame we can map those full country names to those rows where we have the corresponding codes. And we can actually do this with the map method. And here we can pass our mapper panda series. And actually, first of all, we filter our Olympics data frame only by the rows where we have missing countries. And we select the code column. So let's simply have a look here. And here we get, for those rows where we have missing values in the country column, the full country names that we have found in our Google search and that we saved in the Mapper Panda series here. So for instance, we have mixed teams, a unified team, and Czechoslovakia. So ZX stands for mixed teams. And finally, we can fill all missing values in the country column with fill NA. And instead of passing only one value, we can also pass here the mapped values. So let's have a look here. And actually, we also pass true to the in-place parameter. And again, let's have a look at the rows where we initially had missing values. And now we have successfully replaced the missing values by the full country names. So for instance, for ZZX, we have mixed teams, and for EUN, we have a unified team. All right, thanks for watching, and see you also in the second part. Bye. Hi, and welcome back to data cleaning part 2, and we still have some missing values in our Olympics data set. So in total, we have 4 missing values in the columns code and country. And to understand why we have missing values, we just filter for those rows or for those medals. And we can see that even the athlete name is pending here for 3 medals. And I suspect that this has something to do with doping, but I'm not 100% sure. But anyway, in this case here, we should simply delete the rows and drop the rows where we have missing values here. And of course, we can do this with drop NA. And we want to drop all rows where we have a missing value in the code column. So now we have removed all missing values, and let's restore the range index. So as we have removed 4 rows, we do not have a range index anymore, but we can restore it with the reset index. Now we have seen before that in most columns we have text data, and with nUnique we can check the number of unique values in the text columns and also in the numerical column year. And actually, for some features, we only have a few different categories. So for instance, for gender or for medal. And whenever we have only very few categories, then it could make sense to convert the data type to category. And now let's do this for the medal column. So we can actually convert the data type to category with S type. And let's have a look with the info method. And here we have now category. And actually this saves some memory, so we have here 2.9 megabyte and before we had 3.4. But you should keep in mind that categorical columns can cause problems in other situations. So I'm always very careful with categoricals. And in my view, the memory reduction alone does not justify a conversion to categorical. So there must be an additional benefit. And having a so-called ordered categorical is an additional benefit. So by default, categoricals are unordered, but we can define an order. And the question is now, why could this be beneficial? And we all know that we can order numerical data from high to low or from low to high. But when it comes to text data, we are limited here. So we can order text data alphabetically, but in many cases, this is actually not what we want. And the medals example is the perfect example for this. So we have the medals bronze, silver, and gold. And we can clearly sort these medals by value or importance from low to high. So we're starting with bronze, and then silver is better than bronze, and gold is better than silver. So here we have a clear order, or we can define a clear order. But now if we try to sort all rows by the medals column with sort values, then the values are ordered alphabetically. So we have, first of all, bronze starting with a B, then we have gold, and finally we have silver. However, the order bronze, silver, and gold definitely makes more sense. So the good news is that we can define an order for categorical data, and there are some specialized methods available for categorical columns, and we can actually access those methods with the cat accessor. And this is similar to the str accessor for specialized string methods. And then we have the categorical method set categories. And here we can define the order from low to high, so bronze, silver, and gold. And we have to pass true to the ordered parameter. And also here, in order to save the changes, we have to set the in-place parameter to true. So let's run here and let's again sort all rows by the medals from low to high. And here we're starting with the bronze, then silver, and then gold. And here we can see we have 3 categories, and these are clearly ordered. So from bronze, then we have silver, and finally we have gold. All right, we have successfully imported, merged, and cleaned our data, and we are starting to analyze the data in the next lecture, so hope to see you there. Bye. Alright, in this lecture we try to find the 10 most successful countries of all times in terms of total Olympic medals, and we will go further into the details and differentiate between summer and winter games, and also between gold, silver, and bronze medals. So we are dealing with lots of numbers, and there's no better way to analyze many numbers than by creating intuitive plots. And the Seaborn library is our tool of choice here. So first of all, let's import matplotlib and also Seaborn as SNS. And we can ignore the future warning here. And still we have saved the merged and cleaned Olympics data frame. And then to get the total number of medals per country, we can simply call the value counts method on the country column. And here at position 1, we have United States with 5,238 medals that were awarded to athletes from the United States. Then followed by the former Soviet Union. Then we have United Kingdom, Germany, France, and so on. Now let's get and save the top 10 countries in the variable top 10. And we simply use here the head method. So in addition, we have Italy, Sweden, Canada, Australia, and Hungary. And we can also visualize this with a matplotlib bar plot. So we simply use the plot method and select bar plot. And these are the top 10 countries. And it's pretty obvious that by far the most successful country is United States. So they have twice as many medals as the second position, the Soviet Union. And then the differences are getting smaller here. This is essentially a count plot because we count the number of medals for all countries. And Seaborn is very powerful when it comes to count plots. So there's a special Seaborn function to create count plots. It's sns.countplot. But first of all, let's filter our data frame Olympics only for those rows where we have medals for the top 10 countries. So we filter Olympics for those rows where the value in the country column is in the top 10. And we create here the subset or the sub-data frame Olympics 10. And we use that data frame in the next minutes to create some Seaborn count plots. So first of all, let's create the most simple count plot. And actually we pass the data frame Olympics 10 to data. And here on the x-axis, we want to have the 10 countries. And here we have Hungary, United States, Germany, and this is actually the order of appearance in the data frame. So it's not ordered from high to low as we have here, but we can also set this. So there's the additional parameter order. And actually, we want to order by the top 10 countries from most successful to least successful. So let's have here the index. And let's run again. And here we have essentially the very same plot as above with matplotlib. And essentially the height of the bars is the total number of medals, irrespective whether these medals were awarded in the Summer or Winter Olympic Games. And it might be beneficial to differentiate between summer and winter. And we can actually do this with the additional parameter hue. And here we can pass addition, so that's a categorical variable in our data frame. And we have either the value summer or winter. And let's run the cell here. And here for each and every country, we have splitted the bars into a summer bar and a winter bar. And still the order of the countries is from United States to Hungary. And here we can see that there are some countries that are relatively better in summer or winter Olympic Games. So for instance, Canada seems to be a winter Olympic Games country. And in contrast to that, Australia and Hungary are clearly countries that are more successful in summer editions. Next, we can switch country and edition, and we can create a count plot where we have first of all the summer medals and differentiated by the country, and on the right hand side the winter medals. So we simply exchange edition and country, and we pass edition to the X parameter and country to the hue parameter. So here on the left hand side now we have the Summer Olympic Games medals, and we can also define the order here within the summer medals. So there's the additional parameter hue order. And also here we pass the order that we have in the top 10. So starting with the United States and followed by Soviet Union, United Kingdom, and so on. And also this graph tells us that Canada is relatively better in the winter editions. And UK here in green is relatively better in summer editions. So before we have differentiated between summer and winter editions, but we can do the same also for the kind of medal, and we can pass medal to the hue parameter, and again we pass the country to the X parameter. So let's have a look here. So we are starting here with the United States, and then we have bars for gold medals, silver medals, and bronze medals. And still we defined that we want to have the top 10 order, and then we passed gold, silver, and bronze to the hue order parameter to have gold first, then silver, and then bronze. And we can also define the colors of the bars. So we have the additional parameter palette, and here we can pass colors. For instance, gold for the gold bar, silver for the silver bar, and as an approximation, brown for the bronze bar. All right. Also here we can switch country and medal. So we pass medal to the X parameter and country to the hue parameter. And first of all, on the left-hand side, we have gold medals. And clearly United States is at the first position. Then we have the silver medals and then the bronze medals. All right, these were some examples of Seaborn count plots, and there are many more options. So feel free to create your own count plots. Thanks for watching, and see you in the next lecture. Bye. In the last lectures, we found out that some countries are more successful than other countries in terms of total medals. And now in this and the next lectures, we try to identify the factors that influence and determine a country's success. And first of all, it's a no-brainer that countries that participated in most of the games since 1896 are more successful than newer countries or less politically stable countries that maybe only participated in 1 or 2 games. So that's a no-brainer, but we are going to test that relationship here. And also we can suspect that the higher the country's GDP per capita, And this measure stands for the standard of living. In easy words, the richer the country, the more successful the athletes. So that's our hypothesis here. And finally, another hypothesis is that a larger population leads to more medals. And also this should be a no-brainer, but we will perform a hypothesis test on this as well in the next lecture. So in this lecture, we have to prepare our data. And first of all, we have still saved the Olympics data frame. And now in our first step, the plan is to aggregate the data frame and count the number of medals per country. So the number of gold medals, silver medals, and bronze medals, and also the total medals. And we can either do this with the group by, or even more simple, in this example here, we can do this with pd.crosstab. And let's have a look here. So actually crosstab computes a simple cross tabulation with, in our example, 2 factors. And the first factor is actually the country factor, and the second factor is the medal factor. So we split the data frame by country and medal. And by default, crosstab computes a frequency table. But we can also select here other aggregation functions, but actually we want to count the number of medals. So frequency is okay here. And finally, we can also calculate the sum over all rows and all columns by passing true to the margins parameter. And we call the total actually here total. So let's create the data frame medals per country. And here we are starting with Afghanistan, and in total Afghanistan won 2 bronze medals and 0 silver and gold medals, and the total number is 2. So this is here actually the sum over bronze, silver, and gold. And finally, in the last row, we have the sum over the columns here. But actually, for our purposes, it's sufficient to have here this aggregation, so we can actually drop the row total. So now we have in each and every row actually one country with bronze, silver, gold, and total medals. And it definitely makes sense to slightly rearrange the data frame and change the order of the columns. So having first the total medals, then gold, silver, and bronze, and then to sort the countries from high to low by total, gold, silver, and bronze. So let's actually override medals per country. And let's have a look at the 50 most successful countries in terms of total medals. So no surprise, we are starting here with the United States, so then we have Soviet Union and so on. And finally, the 50th most successful country is Iran. So now we have here an aggregated data frame with the total number of medals. And now in the next step, we have to add some additional features that we suspect that these features actually determine and influence the total number of medals. And let's recall that we have in the data frame dig the features population and GDP per capita, and with a left join we can actually add those 2 columns here to our aggregated data frame. So let's perform a left join here, and the left data frame is medals per country, and the right data frame is the dig data frame. And actually we want to merge or join on the index of the left data frame and on the country column of the right data frame. And we want to drop the column code. So let's have a look here, and we override medals per country. So here we have successfully added the population and GDP, and we suspect that those 2 features actually explain the total number of medals, so to say the success of the countries. But we also suspect that there's a third feature, and that's actually a no-brainer. A country that participated in all or most of the games should be more successful than a country that participated in only 1 or 2 games. But based on the data that we have, we cannot directly determine the number of participations. So we can only count the number of games where the country has won at least 1 medal. And let's assume that a small country participated in the Summer Olympic Games in London in 2012. and the country didn't win any medal. Based on the data that we have, we cannot actually prove that the country participated in the Summer Olympic Games in London 2012. So we can only count the number of games where the country has actually won at least one medal, but at least for the top countries, this should almost perfectly approximate the number of participations. Now, to count the number of participations, we have to identify all games, and let's have a look at the number of unique values in our columns. And here we have 41 unique values for a city and 33 unique values for the year. But this doesn't mean that we have 41 unique games or 33 unique games, because there are some cities hosting more than just one game, like for instance London, and there are some years where winter and the summer games took place. So we have to count the number of unique combinations between a city and year. And first of all, let's create the additional column games. And here we can simply join the strings in the columns year and city. So let's have a look here. So now we have here on the right hand side the clear identifier for the games. So for instance 1896 in Athens. So here we have a clear identifier. And now we can determine the number of unique events. So we have 49 different games, and we can also count the number of medals per game. And we have over 2,000 medals in Beijing 2008 and also in Sydney in 2000. And now we can group the data frame Olympics by the country. And we can determine the number of participations. So actually the number of unique values in the games column. And here we get a panda series with on the left hand side the country and on the right hand side the number of games. So for instance for Afghanistan we have 2, for West Germany 12 and so on. And that's exactly the feature that we want to have in our medals per country data frame. So we create an additional column, total games. And let's have a look at the top 50 countries. And for example, here we have United States with 48 participations. And actually the only game where United States didn't participate was 1980 in Moscow. Finally, we have here one data frame with the total medals and some features that should influence or determine the total medals, like population, GDP, and total games. And instead of having here the absolute numbers, we can also create the relative ranks for each and every column. And we can actually do this with the rank method. And we pass false to the ascending parameter. So we have rank 1 for the most successful country and the country with the highest population and so on. And here it's getting more clear that there must be some positive relationships. So United States is number 1 in terms of total medals and number 3 in terms of population, number 7 in terms of GDP, and number 1 in terms of total games. And in the next lecture, we apply some statistics and perform some hypothesis tests on this data here. So thanks for watching and see you there. Bye. Alright, in this lecture, we are going to test whether the factors population, GDP per capita, and the number of participations influence and determine a country's success in Olympic Games with statistical significance. So population is a metric for the size of a country. GDP per capita is a metric for the wealth or the standard of living, and the number of participations is an indicator for the political stability. So in simple words, we are testing whether the relationships between size and success, wealth and success, and political stability and success are just random or statistically significant. And actually, this isn't a course on statistics, and therefore I will keep the statistics part as easy and as intuitive as possible. And essentially, we will calculate correlation coefficients and test whether these coefficients are significantly different from 0. So a correlation coefficient of 0 indicates no relationship. And in case we can reject the hypothesis that the correlation coefficient is equal to 0, we can conclude that there is a relationship. So still we have saved the aggregated data frame medals per country with the total number of medals and the features population, GDP, and total games. And for our purposes here, we can drop the columns gold, silver, and bronze. So we only care about the total number of medals, irrespective whether it's gold, silver, or bronze. So let's have a look here. Now we only have the total medals, population, GDP, and total games. And actually, when talking about the correlation coefficient, typically we mean the Pearson correlation. And we can actually create the correlation matrix with the core method. And the default setting is that we get the so-called Pearson correlation. But let's do this here more explicit. And we pass Pearson to the parameter method. And here we have the correlation matrix. And actually the correlation coefficient can take values between -1 and +1. And -1 indicates a perfect negative correlation and +1 a perfect positive correlation. And a value of 0 indicates no correlation. So let's focus on the total number of medals. And of course, there's a perfect positive correlation with itself. And there is a positive correlation of 0.2 with the population and a positive correlation of 0.43 with the GDP and a pretty high positive correlation with the total games, so 0.71. So that's the Pearson correlation, but the Pearson correlation is quite restrictive and it only assesses linear relationships. And statistical tests actually assume that both the variables are normally distributed. So if we consider the Pearson correlation between the features, the total medals and population, we actually assume that the feature here, so the column, the values are normally distributed and also the population. So this is pretty restrictive. And in our case, it's more appropriate to work with the so-called Spearman rank correlation coefficient, which assesses monotonic relationships, so whether linear or not. And statistical tests actually don't assume normally distributed variables. So the Spearman rank correlation is less restrictive. And we can calculate the Spearman rank correlation by passing Spearman to the method parameter. And here we can observe even higher correlation coefficients. So 0.4 and 0.92. So what's the Spearman rank correlation coefficient and how does it work? And actually the Spearman rank correlation coefficient assesses the relationship between the rankings of two variables. So not the absolute values, but the relative rankings. And actually the Spearman correlation between two variables is equal to the Pearson correlation between the rank values of those two variables. So we can actually split the operation here into two parts. And first of all, we can calculate the rank values with the rank method. So this is nothing new. And here we have for the total medals rank 1 for United States and for instance for GDP rank 7. And then by applying the Pearson method, we actually get the Spearman rank correlation. So essentially here we should get the very same numbers as above with the Spearman method. So there are minor differences and I don't want to go into details here. So essentially these numbers are the same. So to sum up, the Spearman rank correlation is more appropriate for our purposes. And now we can perform hypothesis tests. And we can do this actually with SciPy and the stats package. And first of all, let's check the relationship between total medals and population. And our first hypothesis is that there is no relationship between total medals and population. So to say, the Spearman rank correlation coefficient is 0. So that's the hypothesis that we want to reject. And we can actually calculate the Spearman rank correlation coefficient and the so-called p-value of the test with the stats.spearman_r. And we actually pass the column total and the column population. And also we have to determine that missing values should be omitted or ignored by passing omit to the NaN policy parameter. So here we get the results of our hypothesis test, and we get a correlation coefficient of 0.419. So this is the same as above here. And in addition, we get the so-called p-value of our hypothesis test. And this is actually here times e to the power of -7. So this is essentially very close to 0. And the question is now, what does the p-value tell us? And let's go here inside. And the p-value roughly indicates the probability of an uncorrelated system producing datasets that have a Spearman correlation at least as extreme as the one computed from these datasets. So in simple words, assuming that there's no relationship between total metals and population, it's pretty unlikely that we get the extreme outcome like this simply by chance. So there's actually zero probability, more or less. And actually we can extract the correlation coefficient R and the p-value separately. So this is R, and the rounded p-value, it's very close to 0. And therefore we can reject our hypothesis 1. And we can conclude that there must be a significant relationship between total metals and population. And it's pretty likely that this relationship is positive. So the larger the country, the more successful in Olympic Games. And now let's come to our second hypothesis. So there's no relationship between total metals and GDP per capita. And also here we use stats.spearman R. And actually our features are total metals and GDP. And again, we get here the correlation coefficient of 0.45. And also here the p-value is very close to 0, indicated by the e to the power of -7. And we should reject also hypothesis 2, and we can conclude that there is a significant positive relationship between total metals and GDP per capita. And last but not least, let's check the relationship between total metals and participations. And we've already seen that the number of games is only an approximation for the number of participations. And in particular for the most successful countries, it's a very good approximation for the number of participations. So it's pretty likely that these countries won at least one medal if they participate in an Olympic game. So let's take the top 50. And again, we can use the stats.spearman rank. And we pass the columns total and total games, so total medals and total games. And we calculate the correlation coefficient, which is very high, 0.68, and also the p-value. And again, here we can see that this is pretty close to 0. And therefore also here we can reject the hypothesis, and we can conclude that the relationship between total medals and the number of participations is significant and probably positive. So our conclusion is that size, wealth, and political stability do matter, and they positively influence and determine a country's success in Olympic Games. Alright, thanks for watching, and see you also in the next lecture. Bye. In this lecture, we will again aggregate the Olympics dataset and count the total number of medals per country, but this time we differentiate between Summer Games medals and Winter Games medals, and also between medals awarded to male and to female athletes. And I suspect that some countries are relatively better in Summer Games or Winter Games. And for some countries, I suspect that male athletes are relatively more successful than female athletes. So we have still saved the Olympics dataset or data frame. And again, we can create a cross tabulation. And this time the features are country and edition, so summer or winter. And we save the resulting data frame in summer versus winter. And let's have a look here. So here we have for each and every country the Summer Olympic Games medals and the Winter Olympic Games medals. And the same we can also do for the gender. So again, we split by country and by gender. And here we get the data frame men versus women. And finally, we can concatenate both data frames and we create the data frame medals by categories. And for instance, Argentina won 259 medals in summer editions and 0 medals in winter editions. And obviously, male athletes are more successful than female athletes. And finally, we can also get the total number of medals. So we create the additional column total and simply add the summer plus winter. And then we can also sort the data frame by the total medals. So starting with the most successful country, and of course it's United States. Here we have the absolute values, so the total number of medals, but these aren't really meaningful and comparable since there are way more Summer Games medals than Winter Games medals, and historically also way more male events and male medals than female events. So we could come to the wrong conclusion that the United States is way better in Summer Olympic Games than in Winter Olympic Games, but that's not true. And in order to compare relative success, we have to use rank values instead of absolute values. And therefore we create the data frame ranks and we use the rank method. And again, we pass false to the ascending parameter and we use the average method. And the average method simply does the following. So let's assume that rank 1 is shared by 2 countries. Then both countries get the average of rank 1 and rank 2, so rank 1.5. So let's create the data frame ranks. And here we can see that United States has rank 1 in all categories. So Summer Olympic Games, Winter Olympic Games, female athletes, male athletes, and also total medals. And actually, for our purposes, we are only interested in the top 50 countries in terms of total medals, because the ranks of smaller countries can be distorted by 1 or 2 extremely successful athletes. So let's focus on the top 50. And we can actually create a Seaborn heap map with the ranks for the 5 categories here. And here we have on the x-axis the top 50 countries, and on the y-axis the 5 categories. And we can see here in the colors the ranks, so starting with rank 1 and deep green and ending at rank 120, deep red. So let's go here inside. And for instance, United Kingdom has the 3rd rank in terms of total medals. But if we have a look at women versus men, then we could conclude that male athletes are relatively more successful than female athletes. And also when we consider winter versus summer, we could conclude that United Kingdom is a Summer Olympic Games country. So this was a very fast analysis, and we will go much more into detail in the next lectures. So hope to see you there. Bye. In this video, we try to find countries that are relatively more successful in summer games and countries that are relatively more successful in winter games. And we try to identify some reasons for this. So the geographical and the climatic conditions might determine or at least influence a country's success in summer and winter Olympic games. We have still saved the data frame top 50, and we can sort the countries by the success in Summer Olympic Games. So starting with rank 1 United States, then we have Soviet Union, United Kingdom, and so on. And we can also directly compare this to the success in the Winter Olympic Games. But first of all, we can also sort by winter. And again, we are starting with the United States, but then we have Canada, Norway, and also Soviet Union. And actually, to compare summer and winter performance, it definitely makes sense to visualize this in a Seaborn heat map. So first of all, we are sorting the countries by summer, and here we have summer, and we have United States, Soviet Union, and here in the winter row we can see and identify the countries that are relatively more successful in the summer. So for instance, United Kingdom, or also Australia, Hungary, Romania. Then we have Brazil, Cuba, Argentina, and so on. So to be successful in Summer Olympic Games, it definitely helps to have a long and warm summer, at least in parts of the country. And also a connection to an ocean might help. And now let's also sort by winter. So we are sorting here by this row. And then we can identify countries that are relatively more successful in winter games. For instance, Canada, Norway, Austria, and the Czech Republic. So these are countries with a long and cold winter and high mountains, and not necessarily with a long and hot summer. And we can further analyze this by subtracting the winter ranks from the summer ranks, and actually sort the values from low to high. And here we have a value of -70 for Brazil. Then we have Cuba. So these are obviously the summer countries. And finally, at the end, we have here the winter countries. So let's save the Panda series here in the variable rank differences. And then we can also visualize this also with a Seaborn heat map. And here we have in red the summer countries. So starting with Brazil, Cuba, Argentina, India, and so on. And on the right-hand side, we have the winter countries like Switzerland, Austria, or Czech Republic, and also Finland, Norway, and so on. And here in this area, we have those countries that are equally successful in summer and winter games. And here we can find the United States, Germany, Soviet Union, and so on. And these countries have one thing in common. They have geographical and climatic diversity. So there's a long and hot summer, at least in parts of the country. And on the other hand side, there's a long and cold winter with lots of snow, at least in parts of the country, and also some high mountains. And also most of these countries here are connected to the ocean. So we can conclude that geographical and climatic diversity is the key to overall success. All right, thanks for watching, and see you also in the next lecture. Bye. In this video, we compare a country's success by gender, and there are some countries where male athletes are way more successful than female athletes. And typically in these countries, men and women aren't treated and supported equally when it comes to sporting activities and participation in Olympic Games. And we can only speculate about the reasons for this, but typically it has something to do with culture and or religion. So still we have saved the data frame top 50, and we can sort the data frame by man, and we create a Seaborn heat map. So here we have sorted by the feature man, and we are starting with the United States, Soviet Union, United Kingdom, France, Italy, Sweden, and so on. And the same we can also do by women. And again, here we are starting with the United States, Soviet Union, then we have China, Germany, and Australia. And also here it definitely makes sense to calculate rank differences. So we subtract the women ranks from the man ranks, and we sort the resulting data frame, and we save it in rank differences too. And obviously here we are starting with those countries where male athletes are significantly more successful than female athletes. And finally, we end up with the countries where female athletes are more successful than male athletes. And it's best to visualize this in a Seaborn heat map. And here on the left-hand side, we have those countries where the success is definitely and significantly biased towards male athletes. So we have Pakistan, Uruguay, Iran, India, Belgium, Croatia, Turkey, Yugoslavia, Italy, and so on. And here on the right-hand side, we have those countries that are relatively more successful in female events. But obviously this bias is less significant and less extreme than here on the left-hand side. And we could also conclude that the rank differences here on the left-hand side must be offset by some countries here on the right-hand side. So it's not necessarily the case that countries like China, Romania, and Jamaica give more support to female athletes. And also here in the middle, we can see those countries that obviously equally support and treat female and male athletes. And also here we have United States, Soviet Union, Germany, and so on. And in a way, these countries unleash the full potential. So they support male and female athletes. And maybe there's some unused and unexploited potential in these countries here. All right, thanks for watching, and see you in the next lecture. Bye. In the last couple of lectures, we found out that factors like size, standard of living, politics, culture, and religion, and also geographical and climatic conditions determine a country's overall success in Olympic Games. And in this lecture, we will cover another aspect. And actually, in a country, some sports are historically and traditionally more popular than other sports. So different countries have different national sports. For instance, cricket is the national sport in India, and table tennis and badminton are very popular in China. On the other hand side, there are core Olympic sports like aquatics, athletics, gymnastics, and skiing that have been in every Olympics since the early days. And these are actually the top sports in terms of events and medals. And now the implication is pretty simple. Those countries where the most popular sports match with the core Olympic sports are more successful in Olympic Games than other countries with less popular national sports. And I would call this the tradition factor. And we have still saved the Olympics data frame. And then we can actually get the most important sports by actually counting the medals awarded in the sports. So let's use here the value counts method. And here we can see the core Olympic sports, aquatics, athletics, rowing, gymnastics, skiing, and so on. And also we have here team sports like ice hockey, football, or hockey. And as a side note, in the whole project here, we considered medals on the individual athlete level and not on a team or event level. And that means that we counted all team members and all medals of a successful team, and not just the team as one entity. And in a way, we overrated team sports and team events, but there's no right or wrong, and maybe it's a perfect homework for you to treat team sports differently. So now let's move on. And let's save the sports in the order of importance. And we actually select here the index and save it in the variable sports. And one more time, we can get the most successful countries. So in this example, the top 20, also with value counts. And we save the top 20 countries in the variable top 20. So we have here United States and Soviet Union. And again, we can create a cross tabular with pd.crosstab. And now we split by country and sport. And we save the resulting data frame in by sport. So for instance, for Argentina, we can see 3 medals in aquatics and 5 medals in athletics. And again, instead of having the absolute number of medals, it's more meaningful to have the rank values. So let's override by sport and let's get the ranks for each and every sport. So we have here the ranking data frame with all 145 countries and all 48 sports. But now let's filter by sport only by the top 20 countries. And we also change the sequence of the sports, or the sequence or order of the columns, starting with the most important sports. So actually we pass here sports, and let's actually override by sport, and let's have a look here. And here we have the top 20 countries by total medals. And the most important sports, starting with aquatics. And already here we can see that the United States is the most successful country in the three most important sports: aquatics, athletics, and rowing. And also here it's best to just visualize this. And again, we create a Seaborn heat map. And now the idea is that we only consider the top 5 countries per sport. So we have green for the top country in each and every sport. And beyond rank 5, so starting with rank 6, we have deep red. And again, we can see here that the United States is the top country in the most important sports. And let's compare this, for instance, with the United Kingdom. So in total, United Kingdom is at rank 3, but there seems to be no tradition in aquatics and also in gymnastics and skiing. So that's no surprise, because there isn't too much snow and mountains in UK. And obviously the most popular sports in UK are shooting, sailing, cycling, and also tennis, and canoe, polo, lacrosse, golf, and so on. However, these sports are not the Paralympic sports, and therefore there are not too many medals available for these sports. Finally, let's have a look at another example, and let's consider China and South Korea. And there seems to be no tradition in the core sports like aquatics, but the national sports here are badminton, table tennis, and taekwondo. So this is a pretty interesting image here, and feel free to spend another 5 or 10 minutes and have a look at your country. So thanks for watching, and see you in the next lecture. Bye.